Looks like we made it. Welcome back, folks. Before we get started, I just want to mention that the assignment number 10 that's being slowly built, so far we have section 11.8 posted. We'll have section 11.9 posted soon, and that'll be the entirety of this assignment. The section 11.10 we're going to split over Thursday's class and we return on Wednesday's class, so it won't be on this assignment. Any questions about assignment 10 folks would like to discuss, or questions from the previous homework assignment 9 that's due this Thursday? Okay, let's start our work for today then. So far we've discussed all the tests for testing series for convergence and divergence that we need to cover in this course. And what's interesting about some of the tests that people have remarked about is we have never actually seen this situation happen one time in class so far. I mean, you may have seen it happen in your own homework or experimenting with your favorite series, but we've never actually seen the ratio test fail. That's about where it's going to start happening quite a lot in the sections 11.8, 11.9, and 11.10, where we're going to start dealing with power series. So let's start off by defining what we mean by power series and see how about we can go testing them. So as usual, we'll begin with a working definition. That definition says that a series that has the form, let's write this in a couple ways. Let's write this out fully expanded and then again in sigma notation. But a series that has the form of C0 plus C1 times x minus a plus C2 times x minus a squared plus C3, just to establish the pattern, times x minus a to the power 3 plus. So far, that would be what we mean by a power series. Let's add a little bit more just for emphasis. Like any other series, a power series has infinitely many terms. If you want to really emphasize their infinitely many terms, we can say plus dot 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 all the way to plus c sub n times x minus a to the power of n, and dot 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 once again. So that's our series that we'd like to study. But this is just its fully expanded form. We're once again trying to add together infinitely many terms. Using sigma notation, it will be expressed this way, and this is something for me to get used to. It's traditional to start at 0 on the index for power series. That's for reasons that we'll see in section 11.10. So we'll start at summation 0, go off to infinity, and this would be c sub n times x minus a to the power of n. Let's make that green. And essentially, that power n with the variable x is the reason we call it the power series. The variable x is essentially the only thing that's new about this series. Any questions so far about it? Okay, then the working definitions for things that you'll see quite a lot in the reading and the homework problems are things about the coefficients and the center. So let's write that out next. This is a power series. Oh, I forgot this was a sentence we were working on. A sentence series that has the form, all this stuff, then back to that same thought, is a power series. It's a R there. Centered at A, this value here, with coefficients the entire sequence, c sub n, as n goes from 1 to infinity, will be considered the coefficients. They're coefficients in the usual sense. It's the coefficients of a variable minus a value, or to a power possibly. But it's really an entire sequence in this situation. So that's what we're meaning by a power series. Any questions about it? Okay, if you were to look at this series really carefully, what would be one value that the series must converge on for certain? Kind of a weird question, right?
0.
You have to converge on 0, but remember, convergence is going to depend on the value the variable x itself takes. So what should the variable x itself take on so that we're adding a bunch of zeros and it definitely would converge? Because remember, x can be any real number whatsoever. So if we want convergence, for sure, what should x itself be?
A.
Yeah, if we let it be a, then this whole thing will be 0, and we'd be summing a whole bunch of zeros. CSUM naught, however, may or may not be 0. So we can say if x equals a, which is the center, then the entire power series, summation as n goes from 0 to infinity, of c sub n, x minus a to the power of n, well, convergence divergence of a power series now also depends on the variable x itself. But if x is a, then this is the summation as n goes from 0 to infinity of Cn times 0, which is 0. So this would converge to 0. So that's something that's guaranteed about every power series. Every power series will have a point of convergence, and that happens when the variable takes on its center itself. So that's nice. Then we should say a little bit more things about convergence. Any questions so far about converging at the center? Okay, so another set of common terminology that we're going to see is things like the interval of convergence. So we know for sure if x is equal to a in the power series, we will have convergence. So that tells us that this is something that does exist. And now we ask the question, what is the largest interval of numbers for x such that the thing still converges? We're going to start thinking of that as a domain, but for now we'll call it the interval of convergence is indicated by just an uppercase I. For interval is the largest interval of real numbers x such that the power series converges. So that interval of convergence is something that's going to be referred to in many of these different problems in 11.8, 11.9, and 11.10. We'll be given a power series, and the most important question will be asked right off the bat is, what is the interval of convergence I, and what is the radius of convergence? So we would like to compute the largest interval over which the whole thing will converge. Then this related comment, or related concept is the radius of convergence is half the length of I, where I is that interval of convergence. If you want to say the diameter of convergence, then you would just say it's the length of the interval I. So for example, a quick example with the terminology, if the interval of convergence is say 2 to, let's make it be 5, and if A is say 3, let's make that 2 to 4 to make it symmetric. Then we have a power series that we're saying is centered at A. The interval convergence is from 2 to 4. Then the radius will just be the half of that length. So the length of that interval would be 4 plus 2 divided by 2. So the radius of convergence would be 3 in that situation. We'll do, of course, a bunch of problems top to finish, start to finish. Any questions so far about that? Okay, so our new concept is the power series, where we're inserting a variable x. The new drama that creates is now convergence and divergence. Depends on that variable x, and I is meant to be the largest largest interval, whether it's open or closed, of values of x for which the power series converges. And r is just the radius of that interval. So let's try some problems next to see just what can happen. Any questions at all so far, the working definitions? Okay, so let's go off to a set of problems that will use this. Sadly, we have to let something go. Let's get rid of this definition first. Maybe leave that, since that's our power series, centered at A. And this is what the instructions are going to look like for this new set of problems. It's going to say to determine the interval. My R's are not the greatest lately. There we go. Interval and radius of convergence. So what's very interesting about these problems so far is when you're given a power series, the question is no longer if it converges, because it will always converge at the center, x is equal to a. So now the question is, what is the largest interval of convergence and what's its corresponding radius? So let's start off with something along these lines. It'll be the summation as n goes from 0 to infinity of -1 to the power of n multiplying x to the power of 2n divided by 2n factorial, where the parentheses should go first, then the factorial. Okay, so we want to determine what is the interval and radius of convergence for this function. First, just to wrap up our concepts, what would you say the center of this power series should be? Well, this one was centered at A itself. So given this form, what would you say it should truly be centered at this time? Any guesses?
-1.
Close, not quite. It has to go on with whatever is around the x. So what we could do is rewrite this as summation as n goes from 0 to infinity. I would ignore that even power 2n, that's kind of a red herring here. But we can rewrite this if you like as -1 to the power of n. And would you folks agree that this is something you could always do? X to the power of 0 to the x minus 0 to the power of 2n divided by 2n factorial. It's a bizarre algebraic step, but would you agree that that's a valid algebraic step? So that would tell us that if we rewrite it in this form, this is a power series centered at 0. So it definitely converges at 0. Our interval then is going to be centered at 0 itself. And we want to know how far away can we get from 0, the variable x, until we suddenly switch over to diverging. And for how long is this whole thing going to be converging? So far if I put in a 0 at x, the whole thing is zeroed out and it'll converge. I might wonder, can we put in point 1, for example? Would it converge or would it diverge? So this seems like a terrible problem in the sense that there's infinitely many different series we're looking at when we consider a power series, and all of them depend on the choice for the variable x. Nonetheless, we have a test that will take an entire series or power series and determine whether it converges at what interval. So we're going to use the good old ratio test. Ratio test is usually what you would think of using anytime you have a power series. And especially since there's things that are factorial as well, it'd be a great test. So that's where we'll start. So by the by the ratio test, we have convergence when, and we'll come back to this. So let's leave this blank. You might want to drop a few lines down in your paper, and we have to actually do that ratio test. So let's do it maybe over here. We need to know what the limit as n goes to infinity of the absolute value of a n plus 1 divided by a sub n comes out as. So let's just go through the forms, write down the format for this limit. It's the limit as n goes to infinity. We'll throw in the absolute value, and this is our a sub n. Not the summation part, just the nth term would be all of that in the fraction. So if we're taking the absolute value, however, the -1 to the power n plus 1 would be wiped out. So if you didn't write that in, that'd be okay. You still need absolute values, however, because we have x to the power of 2n plus 1, and whether this is positive or negative now depends upon x itself. So the absolute values are still necessary due to the variable x that entered the problem. So that's x to the power of 2n plus 1 written this way. That's another mistake to be wary of. When n changes to 2n plus 1, we also have a distributive law to be very wary of. Then down below, it's the same kind of situation. We have a 2, n is replaced with n plus 1, so we have a distributive law, and factorial there, with a bracket, just to be clear. So that's the an plus 1 altogether. Does that look all right to folks so far? Okay, then the whole thing is divided by a sub n. So we're going to multiply by the reciprocal, our standard trick, and then simplify everything inside the limit. So this is multiplied by the reciprocal of this a sub n. So we'll have 2n with parentheses, then factorial, divided by x to the power of 2n. Then all in absolute values. So now we're ready to start computing. Any questions so far? Okay, maybe for this one, let's take an extra step to just simplify the an plus 1. Since this is a bit of a mess, we could say that this is the limit. As n goes off to infinity of absolute values, we could also write, say, x to the 2n plus 2. Or you could write x squared times x to the 2n in anticipation of a cancellation, divided by, then let's do this one in the margin, since that one looks like a bit of a pain. We have 2 times n plus 1 factorial. This is coming from the an plus 1. So if we distribute, this is the same as 2n plus 2 factorial. And if we want a format, which will cancel easily on the next step, then we can re-express this as 2n plus 2, the base of the factorial, descend by 1, so it's 2n minus 1. Then it's 2n factorial, and, 2n plus 1, since we descended by 1, then 2n plus 0, or just 2n factorial. Then we can stop right there, since we do have a 2n factorial from the a sub n term. Does that make sense so far with the factorial portion? Okay, this is probably good to do in the margin, because rewriting the limit this many extra times is just tedious. And for a reminder, whenever you see things like 6 factorial, all you're doing is taking 6 times 5 times 4 times 3 times 2 times 1. But we have other things like 2n factorial over here. So they could think of this as 2 by 3 factorial as an example. But now we have a 2n plus 2, 2n plus 1, a 2n factorial, that's simplifying the denominator of a sub n plus 1, and the rest is just copying it in. The next one is 2n factorial divided by x to the power of 2n, all in absolute value. Now we're ready to finally start canceling. But first, does that look okay to folks to that step? Okay, so let's start our cancellations. First things that cancel is the entirety of x to the power of 2n is gone. Now let me know how this looks as a step for canceling. All I'm going to get is an x squared, so I'd cancel it in that way. Does that make sense to folks for visualizing it in that certain way? Okay, so with that cancellation, just x squared is surviving. Then we have 2n factorial, canceling with this 2n factorial. 2n plus 2, 2n plus 1 are just going to stay right where they're at. Now we're ready to start working with the absolute values next. So what's going to happen with the absolute values are that they still affect the variable x. X can still be positive or negative because it can be any real number. The only thing that's going off to infinity is the index n. But because n is going to infinity, 2n plus 2, 2n plus 1 is all positive, we can write this as the limit as n goes to infinity of just 2n plus 2 times 2n plus 1. Then the absolute value bars are going to collapse to the only portion that has a possibility of coming out negative. And that's exactly, well, not exactly, it's sort of here, absolute value of x squared. Well, by a fluke, the power 2 is even, so that's also always positive. And if you drop the absolute value bars, in this situation, you would have been okay. But for x cubed, just be really careful. You may need the absolute value bars. Any questions so far? Okay, this is a weird thing to say, but the next step is unnecessary in this problem, but it might be a helpful way to visualize in other situations. One thing I'm allowed to do on this limit is write that this is the limit as n goes to infinity of 2n plus 2 times 2n plus 1 over 1, and I can take the x squared. We can now drop the absolute value bars, if we'd like, just immediately, and that can be pulled clear outside the limit in this way. This is something that we possibly have never done before in class. Anyone see why x squared can commute clear outside of the limit in this situation? In other words, what's special about x squared, and what's special about 2n plus 2, 2n plus 1, that forces me to keep 2n plus 2 exactly where it is, but I can just completely pull out an x squared.
Well, it's isolated and it's in the numerator.
So it's isolated in the numerator, that's important, but there's still one important feature that was allowing us to take out x squared, but other problems were prevented. Yeah, go ahead. Exactly, with respect to this particular limit, which depends on a variable n, x squared is in fact constant. And the limit of a constant is always the constant times the limit. So the constant law applies to this. Again, it doesn't have to be used, but it can be a powerful tool for visualizing and other problems. So that's a legal step to take. Yeah?
So if it was like still 1 over x squared, could we still pull it out?
You could still pull it out, correct. The only thing that would keep x squared banished to inside the limit is if the limit depended on x. Then x squared cannot move at all, and we could factor out to the 1 over 2n plus 2 times 2n plus 1 outside, like you're mentioning. So it's all about what is happening with this variable, what is actually going to infinity. But now that we've pulled out x squared, other questions or comments about that? So this is helpful for visualization because it just makes it easier to see what the limits are without the noise of dealing with extra variables like x squared that are in the picture. So what would be the value of the circled limit?
0.
Yeah, we have a rational function as a horizontal asymptote, y equals 0. So this is x squared times 0. So we've done it. That's the entire limit in the ratio test. And a variable times 0 is still 0. Variables aren't immune from that. Now we go to the ratio test. The ratio test says if you take the limit like we just did, you got a value L, which is not infinity, or negative infinity, and it's less than 1, then the series is absolutely convergent. So by the ratio test, we have convergent when x is any real number. Because no matter what happens in this limit from the ratio test, x can be anything. You could say x is a trillion, and in the limit with the ratio test, it would have been a trillion times 0, so we have that that's less than 1, or convergence. So in other words, convergence was not affected in any way by whether x was one value or another value. It can be anything whatsoever. So that's kind of cool. It causes problems, however, because if we have x as any real number whatsoever, but remember the two things we're trying to answer are, what is the interval of convergence, and what is the radius of convergence? So what would you say the interval of the convergence should be if we said we have convergence for any real number x? Well, the interval of convergence was meant to be the set of all x for which the power series converges, but the power series converges for any choice of x. What is the actual interval of convergence?
Is that negative infinity to infinity?
Yeah, exactly. It is everything. Pick any real number, plug it in right here, don't forget to square it, and then now it's going to depend on the index n. You'll get that there's convergence of that power series. So if that's the case, if the interval is from negative infinity to infinity, and the radius of convergence is supposed to be this length divided by 2, this it has undefined length, what's the best way to say the radius of convergence should then be in this case?
Infinity.
We just call it infinity. I mean, that's not a number, but it expresses what happened in this problem. This is really the best case for a power series. No matter what you choose for the variable x, you'll have convergence. But there's other cases that can happen. We have a trichotomy, where it's either going to converge for all real numbers x, like what just happened, or it could converge for certain numbers in an interval, so we find its interval of convergence, or it possibly only converges at its center and nowhere else. So that would be the only 3 possibilities that could ever happen. Any questions with this problem so far? Okay, so the very next section we should mention, just to say where all of this is going, the very next section is representation of functions as power series. Then 11.10 is going to be Taylor series and Maclaurin series. This is in fact a Maclaurin series, which we can test just using the tools that we have so far. And we'll say that it's the Maclaurin series for cosine of x. So this is what we're trying to do towards the end of chapter, get power series representations to common functions, so that we could use those representations to solve cool antiderivative type problems. Another neat stuff. Let's go off to another one. Unless there's any questions first with this method so far. Okay, so this next one is going to be kind of a quicker one, I think. Here we're going to test the convergence, divergence, or find the interval of convergence rather, of the summation as n goes from 0 to infinity of n factorial times x minus 3 to the power of n. So that's our new power series. So this is a power series centered at x equals 3. So we have for sure convergence precisely when x is 3 itself. But again, the question is, what is the largest set as an interval of real numbers for which convergence still applies? So once again, we just hit it with the ratio test. So let's do that next. Questions before we start at all? Okay, so here I'll write the ratio test. Just as a way for myself to personally organize what test we're about to use. That might get redundant after a bit. But let's say by the ratio test, we're taking the limit as n goes to infinity of the absolute value of an plus 1 divided by a sub n, which is now the limit as n goes to infinity of a whole bunch of stuff. This is where the algebra gets interesting. But let's maybe take a moment to look before we leap. If we look at where the factorial is, anyone have a prediction of what this is going to do to the interval of convergence? One thing to compare it to for that prediction is, over here the factorial portion, it was 2n factorial, this was in the denominator and it caused the interval of convergence to be all real numbers. So if you put a factorial in the denominator, this is a very common feature, unless you have something competitive in the numerator that's throwing it all off. However, this time, there's nothing in the denominator to control the growth of this thing. Factorial is in the numerator. So would you folks agree that the interval of convergence is probably really, really small? Yeah, that factorial in the numerator is something that's going to cause a problem. So this is going to be very tiny. It could possibly have just one single point. But that's what the ratio test is going to tell us. Mathematically and rigorously, once and for all, that factorial in the numerator is going to cause some problems. So we'll take the limit as n goes to infinity of, first it's an plus 1. So we put n plus 1 here inside the factorial, but n plus 1 factorial is also n plus 1 times n factorial. So replacing this with a plus 1 gives us this quantity, which we throw in inside the limit. N plus 1 times n factorial. That's divided by, multiplied by x minus 3 to the power of n plus 1. And this feels weird, but that's the entirety of n plus 1. So it just comes on one line this time. We don't have to multiply by a reciprocal. We're just going to put in the line a sub n as the denominator. It's kind of a rare treat this time. So a sub n is all of this, and we can write n factorial times x minus 3 to the power n. And we're ready to cancel. Any questions first before cancellation? Okay, so once we cancel, n factorial would be gone. X minus 3 to the power of n cancels the x minus 3 to the power of n in the numerator, and just leaves an x minus 3 overall to power 1. So that's the rest of the limit, and the next step is just to make this look a little bit nicer. This is the same as the limit as n goes to infinity. We have n plus 1 that's alive, but that's always a positive quantity as per the limit. So I'll do n plus 1. It multiplies x minus 3, which is still alive, but x minus 3 is still in terms of absolute value. So it must copy in this way. I think that's probably one of the more subtle mistakes to make on this. It's very easy to forget the absolute values on the variable x, but keep in mind x can be positive or negative, so that has to be there. Then if you like, x does not depend on the variable, the limit. So we can say that this is now x minus 3 times the limit as n goes to infinity of n plus 1. So we're just about there. Any questions to get to that step in the limit for ratio test? Okay, so once we've gotten here, once we've done all the cancellations we can, what would you say the value of this limit must be?
Infinity.
Yeah, we have infinity, and this can take on any value whatsoever, but it's always going to be a constant. So this is not an indeterminate form whatsoever. The whole thing is just infinity. Since a positive constant, multiplying something that's growing larger and larger in the limit would just give us an infinity overall. Provided x, because remember x varies, x is not 3. If x was 3, the whole limit would be 0. Would you folks agree with that? Okay, so let's go back to the ratio test. The ratio test tells us, in case 2, if the limit comes out as infinity, like we just got, then we have divergence. So we're being told here that the power series diverges whenever x is different from 3. This is really kind of the diametrically opposed case over there. Over there, x could have been any real number whatsoever in our first problem, and we had convergence. Here, there is always convergence at the center, so that's never really a question when we do the ratio test. We're really considering x not to be 3 in that ratio test, but it came out to infinity, which is divergence for the conclusion. So now we're going to say by the ratio test, power series diverges whenever x is not 3, and we have the ratio test on there. So this is our conclusion. Therefore, what would you say the interval of convergence should be in this case? This is yet another kind of funny problem. Is interval even the right word? Or what is the only number it converges on?
3.
It only converges on 3, the center. So here we really don't have an interval that contains a single point. We would use set theory curly braces. So the interval of convergence is a bit of a misnomer. It's a set that contains the single number, the center of the entire series. So if that's the case, what would you say the radius of convergence should be in this other odd situation? It's kind of different, right? We don't really have an interval we can compute a length of like this. We had something over here that was infinitely long, so we said the radius is infinity. Over here we have just a single point, so what should the radius then be in this case? Any guesses? Not quite. You're on the right track. You're actually very close.
3/2.
1/2, 2. Well, you're getting colder. You're getting colder, but I appreciate the guess. It's always good to participate. Just throw
0?
something out there. Yeah, it turns out it's 0, exactly. The reason for that is we think of the interval, it's really not an interval, as being 0, 1, 2, 3. We want to know the radius of not quite interval, just a single point. Well, that's kind of an undefined thing. So in this case, where the interval of convergence was just a set with the center, we'll just say the radius is 0 in that situation. Whereas in this case, where the interval of convergence is the largest possible set, all real numbers, we'll say the radius is infinity in this case. And then there is a middle ground for our trichotomy. The interval of convergence can be a bona fide interval, maybe say 3 to 5, which would give us maybe a more interesting radius next. So let's do that as our very next problem. Any questions so far with these last two? Okay, so this last problem, that was the actual power series Maclaurin representation of cosine x. This one, well, it's not very special. It's the 0 function when x is 0. You get just 0. And it's undefined for every other value of x. So a lot of these have no names whatsoever, but that's okay. Let's go off then to the third interesting case that can occur. So instructions are still to just determine I, the interval of convergence, and R, its radius. And for this one, let's take a look at how about the summation as n goes from 1 to infinity of x minus 2 to the power of n divided by n squared times 5 to the power of n. So really kind of the same thing we've been looking at before. Now, again, the only reason this series is 11.8 is purely due to the x and nothing else. Question? Yeah.
Didn't the series have to go to 0? N equals 0?
Oh, yeah, I should have started at 0. Thanks for mentioning that. That is really a struggle for me to get that lower index right. Thanks for spotting that. Other questions so far? Okay, so starting at summation 0, that's something to get used to over the next few sections. One thing that I wanted to mention is on the homework, assignment number 10. Oh, I forgot to put it on there. I could need to make a modification to assignment number 10. Some of the problems are going to be worth 5 points as usual, but some of these problems are going to be worth 10 points. And I'll add an extra note on this assignment to say which ones. This would be one of those kinds of problems that's worth a little bit extra, just because it's really double the amount of work of the last problems we've seen. So in order to test this for convergence divergence, depending on the value of x, once again, we hit it with the ratio test. So if you didn't tell me that you use the ratio test on these problems, that would be okay because, I mean, that is the method. Hit it with the ratio test and see what happens. And there are exceptions, which we'll look at as well. So we're going to take the limit as n goes to infinity of absolute value an plus 1 divided by a sub n. So this is now the ratio test. Let's just go ahead and state it anyways. So this will be the limit as n goes off to infinity of, first we'll do the n plus 1. So this is x minus 2 power n plus 1. N squared will become n plus 1 squared, and 5 to the n will become 5 to the n plus 1. Really not a huge number of amount of copying. Then we're dividing by a sub n, which means we're dividing by this entire thing, so we'll multiply by the reciprocal, which is n squared, 5 to the power of n, divided by x minus 2 to the power of n, and close absolute values. So this is the start of the ratio test. I mean, we probably have done it about 10 times so far. And let me add something a little extra to this. I should start off by saying the summation as n goes to 0 to infinity of a sub n is all of this. That's just going to be handy down the line when we're midway through the problem to have something to refer to as the original power series. So that's the only purpose of adding that. Now let's get through the limit. First, the fun part is the cancellations. X minus 2 to the power of n leaves just x minus 2 to the power 1. We can't do anything with n plus 1 squared versus n squared, but we can cancel the exponential function, base 5. 5 to the power of n leaves just 5 to the power 1 in a denominator. So I think that's all the cancellations. Does that look all right to folks? Okay, so now we'll allow the absolute value bars to collapse in on the only thing that could be negative, which is right here. So we can take the absolute value, still we have the limit as n goes to infinity, of the absolute value, x minus 2, then this whole thing is divided by n plus 1 squared, and it's also multiplied by n squared. So I didn't really achieve much except we maneuvered the absolute value bars, so it's affecting the only thing, the possibility to go negative, and just copied everything after cancellation.
What about the 5?
Oh, and I forgot some stuff. Thanks for this 5 right here. So there's still a 5 alive. Is there anything else still missing? Okay, thanks for spotting that. So now we have, if we'd like, an optional step that says this portion right here, x minus 2 divided by 5, in absolute value, is completely unaffected by the index n. So we can think of this as being x minus 2 divided by 5, multiplying the limit as n goes off to infinity of n squared divided by n plus 1 squared. And at this point in the course, I think you can really start to see why it is a really, really powerful shortcut to know how to eyeball this and see the limit by inspection. Since these things just come up way too often, it's good to have a shorthand for getting through them. So anyone see the value of that limit? No L'Hopital's rule, just eyeballing it?
1.
It has to be 1, exactly. And that reason is because if we squared the denominator, it would be the limit as n goes to infinity of, down below, n squared plus 2n plus 1. And those coefficients of 1 that belong to the n squared term, due to that tie in the rational function, is what forms the limit. So the whole limit is 1 over 1, or just 1. So this is equal to x minus 2 divided by 5 times 1. Or in other words, it's x minus 2 in absolute value divided by 5. So this is interesting because usually when we took the limit on the last two problems, in the first case we got 0, and that 0 did not depend on x, so the radius of convergence was infinity. In the second case, we have that the limit is infinity, provided x was not 3, and so the only point of convergence was 3. This time we get x minus 2 divided by 5. So we have to ask ourselves the interesting question, I think, of when does this converge by the ratio test? So the ratio test was using this limit. What do we have to say about x minus 2 divided by 5 in order to have convergence?
Has to be less than 1.
Yeah, exactly. We go back to the ratio test. We are looking for convergence, and that is this case right here. So we can say by the ratio test, we have convergence when that is less than 1. Does that make sense so far? Let me add maybe a wrapper here. So by the ratio test, we have all this. We have convergence when the limit is strictly less than 1. But our limit also involves x minus 2 divided by 5 in absolute value. So let's carry that up to the next step. Any questions at all so far, folks? Okay, so when we get to this stage, we're just about ready to determine what the radius of convergence should be, but not the interval of convergence, which is interesting. So this time we can say we have convergence when x minus 2 in absolute value is less than 5. So all I've done in this new inequality is just multiply both sides by 5. This tells us at this stage already that the actual radius of convergence is 5 itself. So as soon as you have something in this form, as long as there's no multiplications on x, then the distance from x to 2 has to be less than 5, would tell us the radius of convergence. That's something we can also double check after we get the interval of convergence next. Any questions to that step so far? Okay, so this is what must happen for convergence by the ratio test, but this inequality is equivalent to this one, and this as an inequality is equivalent to negative 5 is less than x minus 2 is less than positive 5. So if I took the absolute value of this triple-sided inequality, we recover the original absolute value version. Then we add 2 to both sides. Not both sides, but all 3 sides. That's a 2. And we get negative 3 must be less than x, which must be less than 7. So that's precisely where we'll get convergence. Any questions about that so far? Okay, here's another problem, however. We still do not know the interval of convergence because of part 3. The test will always fail in this specific case. Whenever we have a limit that comes out and still the variable x is involved in that limit, we can say, well, what happens when this is actually equal to 1 in the limit? So let's let x take on certain values. If x is equal to negative 3, negative 3 at this point is a boundary point, but it may or may not actually be in the interval of convergence. So this is what the interval of convergence looks like so far. It will involve a negative 3, it will go up to a 7, but here's my problem. I don't know if I need to put a parenthesis, which means the power series diverges at negative 3, or a bracket, which would mean the power series converges at -3. So that's what we're looking into right now. So first let's investigate what's going wrong if x is -3 at that boundary point of the interval of convergence. If x is -3, then the limit as n goes to infinity of an plus 1 divided by a sub n, it's still equal to this. Because, I mean, we're still going to do the same algebraic steps. We're just going to evaluate x set to -3 at the next step, as per this. So it's going to be x minus 2 in absolute value divided by 5, which would become -3 minus 2 in absolute value divided by 5, which is 5 in absolute value divided by 5, which is 1. Whenever the limit comes out as 1, that's part 3 of the ratio test, and that tells us no information can be gleaned at limit equals 1 in the ratio test. So precisely at the boundary point of -3, and also at the boundary point of +7, the entire test just fails. That's horrible, but it is what it is. And that's the reason we also hit the prior test really, really hard. We're still going to have things like the test for divergence, the alternating series test, Pierce series, geometric series, all of that great stuff now has to be applied to the original power series when x is -3, because this test has failed us. That's okay, we did get infinitely many successful conclusions between -3 and +7. So let's go to -3. We take -3, and we're going to plug it into the original power series, which would make it an ordinary series. So once again, if x equals -3, then the original power series, summation as n goes from 0 to infinity of a sub n, becomes the ordinary power series. From n to 0, summation, we have -3 for the variable x, so that would be -5 to the n coming from over here. Same thing we did with the absolute values. That's divided by n squared times 5 to the power of n. So that's what we're dealing with so far. It's just an ordinary power series that we must test for convergence or divergence. So let's go over here. First, let's do stuff with exponent laws. This is the same as a summation as n goes from 0 to infinity. Essentially, every time you have something like this, probably the best algebraic step you want to take in this context is to factor. This is the same as -1 times 5 to the n in the numerator. Since by exponent laws, we can bring this together and say it's -1 times 5 to power n. That is still divided by n squared times 5 to the power of n. So there it is so far. If x takes the value of -3, this would be exactly what our power series would look like. Any questions about that so far? Okay, then you should, whenever you see things like this, simplify your power series as much as possible. That'll help us to pick the correct test. This now becomes the summation as n goes from 0 to infinity of -1 to the power of n divided by n squared. So this is a pretty long problem where we use the ratio test on the original power series. We now know the radius, but we do not know the interval of convergence. We had to pick the boundary point -3, plug it into the original power series. So essentially we had to manufacture our own homework problem from 11.2 to 11.6, and you now must test this for convergence divergence. So that's where we're at. Test for convergence divergence. And we'll do it in the same way that we've been doing in the prior assignments so far. So first thing we have to do is, when we look at that, what kind of a series are we dealing with?
An alternating series.
Yeah, whenever we have something that's alternating, this is what the alternating series test will proceed as. We first indicate the nth term of the sequence b sub n. We want the portion of the sequence that is non-alternating, the largest portion that we can grab. That would be 1 divided by n squared. So let me make that a sentence. Let b sub n be set to 1 over n squared. So now we have a sequence, and we have to check two things. What are the two things we have to check by the alternating series test?
it's decreasing and if the limit of B sub n is 0.
Exactly, yeah. So let's look at first decreasing. We can say this is a decreasing, I'll write DEC as a shorthand for decreasing, sequence. And if you left it just like that, I would consider that just fine. Because if it's obvious that something constant divided by a variable that grows without bound and squared is the situation you have for the nth term, then just tell me it's decreasing to assert it, and I think that would be just fine. If it's not as easy to tell, possibly the first derivative test or an algebraic strategy could be effective. But if it's obvious like this one, just state it and that'd be fine. Does that make sense so far? Okay, so this is definitely a decreasing sequence. Also, the limit as n goes to infinity of b sub n is equal to the limit as n goes to infinity of 1 over n squared, which is 0. And if we're doing the test for divergence, this would be really, really bad. But if we're doing the alternating series test, this is good. This gives us a conclusion that the entire thing is, what would it be? Convergent or divergent by those two steps?
Conversion.
Yeah, as soon as we take the non-alternating portion, we know it's decreasing and the limit is 0, we have convergence. So it converges, and this is what it allows us to do. Because it converged, we can put a bracket right here. If we said diverges, we would have to put a parenthesis, which communicates -3 is not in the interval of convergence. But it converges at -3, so we put it in with a bracket. We're still not done. Now we test x is equal to 7. But once you've done it once, it goes pretty fast for the next one, because you'll see how the algebra should go. Any questions before we try the last boundary point, +7? Okay, so when we put in the last boundary point, again, think of this as redoing problems from 11.2 to 11.7, actually. So let's say if x is equal to 7, then we're plugging 7 back in here, and we'll get a +5 with the 7 minus 2 format. We have that the summation as n goes from 0 to infinity of a sub n will be the summation from 0 to infinity of 5 to the power of n, this time positive, divided by n squared times 5 to the power of n. So this one is quite nice. It's almost a matter of how fast you write all this down. We can cancel the 5 to the n immediately, say that this is the series that goes from 0 to infinity of 1 over n squared. It's almost the same as the last one, except this time it's a p-series, whereas this one was alternating. So we can say here that it's a p-series. The p in this p-series is 2, which is greater than 1, which is the requirement for convergence. And then, because we said it converges, we get to put a bracket on 7 by that work there. So from this, we have this. So finally, that is the work in order to get the interval of convergence. I promised a double check on the radius of convergence, because this can sometimes be a little bit misleading. Anything like a half on the x or a 3 by the x could throw this off. What you can do to check the radius is take 7 minus -3, that would be the length of the entire interval, divide by 2 to get the radius, which is 10/2 or 5. So it checks out. But any questions so far about that very long problem? Yeah.
So, what's the difference between the braces again?
Oh, so when we, oh, hang on, that should have been a bracket, sorry
Okay,
about
yeah.
that. The difference is the brace says we are throwing away 7 for divergence, sorry about that. Bracket means we're keeping it because of convergence. Other questions so far? Thanks for spotting that, that should have been a bracket. How about we try one more kind of like this, since these are definitely the harder versions. Let's try something next that also has funnier things happening on the boundary points. Because if we get brackets always on the boundary points, those would be some terrible examples. But any questions at all first? Okay, so once again, we want a whole new power series. I'll leave that summation as n goes from 0 to infinity of a sub n there, just as a reminder that that is a very good placeholder when we get further into the problem. And this one is going to be the summation as n goes from 0 to infinity of x to the power of n divided by n times 3 to the power of n. Yeah, that's what we're dealing with this time. Okay, so let's go through the motions. If we want to find the interval and radius of convergence, which is the instructions for all of these, first we start off with the ratio test. So we have convergence by the ratio test when, let me put a colon here, this is going to be a really long sentence, whatever this limit comes out as, which we'll take a bunch of steps with, is less than 1. So I'll come back to this sentence. So the limit as n goes to infinity of an plus 1 divided by a sub n, and this is our a sub n. So let's go with plus 1. First, the limit as n goes to infinity should be there. We'll do a n plus 1 to get x to the power of n plus 1 divided by n plus 1 times 3 to the power of n plus 1. So that's our standard thing, recopy a sub n with n plus 1 in every position the variable n appears. Then we're dividing by a sub n, so that's multiplying by n, 3 to the n, times x to the power of n. And we carefully cancel from there on. Does that look all right to folks so far? Okay, so next we cancel, and it's the same kinds of cancellations that we've seen before, where x to the power of n leaves this as x to the power of 1. So now absolute values are going to surround that thing, and 3 to the power of n, a different color would be a good choice, leaves us with just 1/3 from down below, and the limit is just with respect to n over n plus 1. So let's maybe take one extra step. We have the absolute value of x coming from here. It's going to be divided by 3 to the power of 1, so just 3. That's still multiplying by the limit, which is still alive, as n goes to infinity, of n divided by n plus 1. But those again are the all-time best limits ever. What is this limit?
1.
We get a limit of 1. So we move on to just absolute value of x divided by 3. Then we remember that this is one big sentence. So we have convergence by the ratio test when this as a limit is less than 1. Okay, so we're about ready to pick up from there on. But as it stands, what would you say the radius should be from here, this work so far? Would it be 1 or 3? It turns out it should be 3, exactly. So we can tell what the radius is once we get to a form that looks about like this. Just keep in mind, once again, because it's really important, there should be nothing affecting the coefficient of x. It should be 1. And the absolute value should be solved for. So if we go absolute value of x is less than 3, then we have half the problem so far. Radius is now 3. But all the fighting in the problem, once again, is in determining what the interval of convergence actually is. So that's going to be our next step. So by this limit, radius is 3, and we'll figure this out as we go. Let's copy that absolute value of x is less than 3. Well, that should be more of a implies, not an equals. So if absolute value of x is, let's say, less than 3, then negative 3 is less than x, which is less than positive 3. So that tells us what the boundary points should be on the interval of convergence. And we pretty much at this stage know that the interval of convergence looks like this. From negative 3 to positive 3, but we have to come back and decide on parentheses or brackets around these two boundary points. So let's just go left to right, starting at negative 3. We can say when x equals negative 3, then the original power series from 0 to infinity of a sub n turns into summation from 0 to infinity of 3 goes right exactly here. So it's just 3 to the n divided by n times 3 to the n. So 3 to the n times 3 to the n. So I think this is a massively new step with these kinds of problems. Not so much doing the ratio test, but actually looking at the boundary points and coming up with our own power series relative to a specific point. How do you folks feel about this? Does this make sense where the 3 to the n came from? Okay, so if we're all happy with that, then once again, in these kinds of problems, we're expecting these things to reduce. And I mean, we should always be kind of looking out for that when we're testing series, if there is a logical reduction to make. But here we get summation as n goes from 0 to infinity of 1 over n. So what does that say about convergence slash divergence for this power series?
Diverges.
Yeah, this is the divergent harmonic series. So divergent, harm short for harmonic, div short for divergent series. There's really no test to make since this is one of our known diverging series. But because we said it diverges, what should be the symbol here? Parenthesis or bracket?
Parentheses.
Yeah, a parenthesis threw away the point -3 because we diverge there, and that's meant to be the interval of points where the power series converges. So now we test 3 itself. Any questions so far with x is -3? Okay, now moving on to x is equal to +3. When x is equal to +3, or excuse me, this was, oh, we just did +3, didn't we? Well, let's do a one fix on that. When x is +3, sorry about that. Let's maybe highlight that. Critical change you should make in your notes and make this one be negative, which means this should have been a parenthesis going around 3. Sorry, I forgot what sign we were using at some point. So when x is +3, we get the divergent harmonic series. Let's do -3 next. Any questions so far about that correction? Okay, so this time we're plugging -3 here, so we'll get -3 to the power of n altogether when x is -3. Then the original power series, summation as n goes from 0 to infinity of a sub n, becomes summation as n goes from 0 to infinity of -3 to the power of n divided by, we had just a n times 3 to the power of n. And there's a specific step that you can make right here to make this cancellation very, very carefully, but it is an optional step. So if you skip across this step to the very next, that would be okay. Let's show it just for completeness. This can be factored as summation as n goes from 0 to infinity of -1 to the power of n times 3 to the power of n divided by 3 to the power of n times n. So we just did the factoring trick like we did, I think, last problem. Any questions about that factoring so far? Okay, so upon splitting apart -3 to the power of n in this way, 3 to the power of n once again cancels, and now we have the summation as n goes from 0 to infinity of -1 to the power of n divided by n. And now we're in, again, a unique position where this could be an entire problem in its own right. Determine if that converges or diverges using methods of 11.2 through 11.7. However, what happens to this one?
Converges.
Sorry, say again?
Converges.
It converges, yes. This one is the convergent, alternating, harmonic, that's an A series. So that's another one that we've tested and named, and whenever it comes up, you can just assert that it converges. So because of the convergence on this one, at -3, we had convergence, which forces a bracket on -3. So finally, we know exactly wherever this makes sense. We want to later on think of this as an entire function, like cosine x, or we might say down the line that f of x, let's put maybe one big conclusion. By all this work, f of x defined to be the function as n goes from 0 to infinity of x to the power of n divided by n times 3 to the power of n. So this as an entire function, which it is in its own right, it has domain, which is from -3 to +3. So everything we've been doing in 11.8 so far has specifically been to find the domain of a function. That's pretty strange. That's a difficult domain type question. That's going to become par for the course when we go to 11.9 and 11.10. But any questions so far about any of this stuff? Okay, these are some of the largest problems that we'll see most of the semester. So I feel like this is probably a good stopping point. Let's call it a day. If you have any questions, then just feel free to hang around. I'll be happy to help.